In past weeks, we've studied discrete time models, and we will now explore continuous time models. So let's begin with an example. Let's imagine a frog jumps. Also imagine that its position at each second is captured by a photographer. So in this picture, we see the frog at one position, and then somehow it magically appears at the next position, and so forth. And these are the images that a photographer has captured, say, every second. And this is an example of a discrete time model where the frog's height above the ground appears to jump. There's not some sort of continual flow of movement here. All right, so we could imagine that the frog's height as a function of time is a discrete time model. It's measured each second, and there's no in-betweens. Now, in contrast, what's actually happening is the frog is moving in some sort of continual fashion, and in reality, the position at each time is a function of continuous time. So if we watch this video and okay, so here's a video. The frog is going to jump, and we can see that it moves through all the in-between heights. It's not just magically appearing from one spot to the next, right? It's a continuous function of time. Now, a photographer with still frame photography wouldn't capture all those in-betweens. And so this gives you an idea how one single thing, a frog jumping, could be looked at either from a discrete time model or a continuous time model. And certainly if you had a really good camera and you could make those frames maybe every half a second or every millisecond or something, you could get something that starts to approximate a continuous time model. And we're going to use that idea when we start making these connections mathematically between the discrete time models and the continuous time models.